Hello, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics, Unit P4, Electricity and Magnetism. This is the last lesson on the electricity side of things. Today we're looking at domestic electricity, and domestic just basically means household. Okay, so it's how electricity in the house. So as part of that, I want you to describe the difference between AC and DC and describe common household safety features. So this here is AC and DC, which you can see. This okay, it's meant to be a video, it's not playing. So it says here to complete a gap. So mains electricity is how many volts? So this is made in Malaysia and it's the same in the UK, by the way. So it's about 230 to 240 seconds. Okay, so mains electricity is about 240 volts, although officially it's 230, but in reality it tends to be about 240. It is a alternating current and it changes direction 50 times per second, meaning it's got a frequency of 50 hertz. So you can see here, this is DC. It constantly goes in the same direction from positive to negative, if we're talking about conventional current, whereas AC, so a DC is direct current, alternating current, it continuously changes from positive to negative, etc. So here, I've got some diagrams. You've got this on either side. These are AC, alternating current, and direct current. Now remember, DC is always positive or negative. Alternating current is changing between positive and negative. So for the top left here, that's quite a straightforward one. It is DC. This one, positive, negative, it's AC. This one, now it is changing. However, it is always positive or zero. It never goes negative. So this is DC. This one here, AC. Now this one, it looks like an AC. It looks the same sort of shape as this one here. However, it is always negative. So it's DC, direct current. This one here, always positive, even though it looks like a sine wave, just like this one here, but it's always positive, so it is DC, direct current. So rectification is the process of converting an alternating current, AC, into direct current, DC. A single diode can produce a half-wave rectification. They also get full-wave rectification, but you do not need to know about that at IGCSE anymore. So a single diode can produce half-wave rectification. One half of the AC wave is removed because it cannot pass through the diode. So remember, previously diodes only flow in the forward bias. So at the minute, this end is positive and this end is negative. So the current will flow and will get a voltage across the output here. The load just means the output, the device which is using it. So here, it will pass through, and then it switches to negative. There's the path here of the current. So the V out is pretty much the same as V in here. We'll get a small voltage drop across the diode, but we'll ignore that for now. Then it switches around. So now this side is negative. And now the diode is in the reverse bias. So the output, there'll be no current flowing. So there'll be no voltage across the load. So now the output will be zero. And then that keeps repeating backwards and forwards. And what you'll see is when this end is positive, current flows and we get a voltage output. When it's negative, no current flows, so we don't get an output voltage. So the output goes to zero. So this is a sort of a rough form of converting AC to DC, or to use the correct term, to use a rectification. Let's have a look at some past paper MCQs from paper 2. Student draws a graph of AC supply and a DC supply. So we can see here that this is the AC and this straight line here is the DC. Which row shows the correct labels for W, X, and Y? So the label of W, so that is basically the Y-axis, or don't get Y and Y-axis mixed up. That will be the voltage on this axis here. X is the straight line, so that is DC. Y is AC, so the answer is therefore D. So this is a circuit component. What is it used for? So is it to increase the size of the current? No. To emit light when there is a current. So this is a diode, but not an LED, not a light emitting diode. It would have some arrows going off it if it was. It's not that. To change the direction of the current. So it doesn't on its own change the direction of the current. It blocks current depending on the direction, but it doesn't actually change it. So to allow current in one direction only, A is the correct answer. And here you've got a diode, which graph shows how the voltage V across the resistor R varies with time. So it's going to be half positive, half zero. And it's going to be this one here. So that's the first learning objective, describe the difference between AC and DC complete. Now for the second learning objective, describe common household safety features. So an electrical cable contains 3 wires. These wires are made of copper because it's a good conductor of electricity. Each wire is made of a thin strand of copper to keep the cable flexible. Each wire is encased in plastic to stop the wires touching. So that will cause a short circuit. So a short circuit is just where you've got 2 wires touching, so there's no resistance between them. So current will pass between them, which we don't want. It can cause overheating problems and various other issues. Plastic is used as a good insulator as well as being tough and flexible. So the main supply is 3 cables. There is 1 brown, 1 blue, and 1 green and yellow striped. Or stripped, as I've put there. I think I made a typo. So the case is made of a plastic as an insulator because you obviously don't want to touch the case and get electrocuted. And this here is a picture of inside the plug. And you can see that one of the wires is connected to this device here, which is called a fuse. And the fuse is designed so that if the current gets too high, then if there's some sort of problem, if the current gets too high, then the fuse will use the term blows, which basically just means the fuse melts and the circuit is broken. Okay. So the fuse is connected to this wire here, as you can see. So the brown one, also known as the live wire. Okay, so as a quick recap, the current goes an electrical appliance through the live wire. The earth wires for metal cased appliances take away any current to the earth if the live wire comes into contact with the fuse of the casing. If the appliance is on, the current will flow out of the neutral wire to exit the appliance. It completes the circuit. So normally, day to day, the earth wire isn't needed. Oh, sorry, it is needed, but it's not used. It's only if there's a problem, then with something which has got a metal casing, then it's there as a protection device to stop the current from flowing. So a fuse is a safe device which breaks the circuit if the current is too high. This protects the cable from overheating and catching fire. Sockets and extensions that are overloaded with appliances are especially at risk of catching fire. And a lot of people are quite guilty of that. They'll have an extension cable, maybe even plugged into another extension cable of 10 items plugged into it. That can cause overloading, which is dangerous, so you probably shouldn't do that. All UK plugs are fitted with fuses. Fuses are available in a range of amperes, so that basically means current ratings to suit different current values. And we'll have a look at those current ratings in a moment. To point out, not all plugs have all three wires. So places like the USA, they only have two wires, and because they use a much lower voltage, they use about 110, 120 volts. Uh, so the fuse contains a thin wire which melts if the current is too high, which we see here. So we've got a clear fuse where we've got a transparent casing and we've got the actual wire in the middle. This thin wire breaks the circuit once it melts, and so electricity is unable to flow through the appliance. The appliance stops working and any danger is being averted. Fuses act as an early warning system, preventing appliances from being damaged by surges in electricity and warning owners of faults. You should select a fuse rating as slightly higher than the current intended for the device. So you shouldn't use something that's lower, because that means at normal use it will actually blow, so the wire will melt. So you have to use something that's slightly high, but you don't want to be too high, otherwise it's not much use. You can get a surge and it won't melt. So what I've got here is a list of devices with some power ratings. I want you to work out the current and decide which size fuse you're going to use. So you've got the option, the voltage is 240, and the fuses we've got a 1 amp, 3 amp, 5 amp, and 13 amp. So I'll do the first one for you. So power rating is 67 watts for the computer. So the current is 67 divided by 240, which is 0.279. You want to cut a fuse which is bigger than that, so the next one up is 1 amp. Give you a moment to try the rest, and I'll put the answers on. Okay, moving on. So electrical devices can cause you to receive an electrical shock or even kill you, which is known as electrocution. This occurs when electric current flows through a person into the earth, because electricity wants to get to earth. It wants to move away, it wants to dissipate, to use energy sort of terms. It wants to spread out. And the way it does that is to go to earth. So when you have, what you don't want to be doing is touching something and the electricity goes through you, or the current rather goes through you and then goes to earth that way. You want a different way for it to go to earth. So if we look at something like an oven here, which has got a metal casing, so if there was a problem and you touched it, it could potentially electrocute you. This is why we have the earth wire. So the earth wire is connected to earth inside here, and also it's connected to the casing. So if the live wire were to become loose, let's say, and touch the casing without the earth, when you then touch the casing, you get electrocuted. However, instead, the earth is very, very low resistance, so the current instead all travel through earth, which will then be connected to some other safety device, like a fuse or a circuit breaker, which will actually stop electricity running in the house beforehand. But if that failed, it would still be going to earth rather than going through you. So to summarize that, it's important when the appliance has a metal casing to earth it. If the live wire touches the case, the outside will become electrified. The earth wire carries away the current to the earth, which blows the fuse. Here, see here another picture of it. The earth wire carries away the current to the earth, which blows the fuse, although it's usually a circuit breaker these days. It keeps people from getting electrocuted. So there's a little video on how earthing works. I've put this on a few times, a little bit about earthing, just because it's an area where students always tend to struggle. So here's an example of a toaster. So when the appliance is working properly, current travels from the energy source to the appliance along the live wire, and then travels away from the appliance along the neutral wire to complete the circuit. In a faulty appliance, if the live wire comes loose and touches the metal casing, the current is then conducted through the casing. What will happen if someone touches the casing? I think you can guess. It's not good. Touching the casing provides a path for the electricity to flow along and so cause an electric shock. So how does the earthing help? By applying an earth wire, sorry. So now, if the wire becomes loose, you can see it flows out now through the earth wire. And you'll also have a blown fuse. Okay, here's some questions. Pause it, and I'll put the answer on in a few seconds. Okay, and the answers. Okay. That's it for today's lesson. So now you should be able to describe the difference between AC and DC and describe common household safety features such as fuses, earth wires, and they're the main two you should be able to describe. Okay, that's it for today. Thank you very much, and I'll be uploading the next lesson soon. See you. Bye-bye.